Oil burners, um, don't know what to say about these things. Everything is kind of confined. So, unlike natural gas, which comes into our house under pressure, and even though we lower it to 1/4 of 1 psi, same thing with propane, it comes into the house under pressure. Oil does not. All right. Oil is in a tank, and it's just going to be gravity and a liquid that comes through it. Now, and then it'll create a siphon to pull more oil into it. Now, these burners are pumps. So the motor is going to be spinning. It's going to be blowing air into the unit. It's going to be pressurizing that oil as it comes through the pipe, and then once we pressurize the oil, it sends it to a thing called an atomizer. So it creates a real fine, thin mist, mixes it with combustion air from the room that blows in with that, and then we can go ahead and ignite it. We have a lot of surface area that's in there, and we usually get a pretty decently clean burn coming out of these things. When they're working properly, they should be relatively quiet. If you put your hand on them, you might be able to feel them spinning, but you really shouldn't be hearing anything. If you do, obviously we're getting bad bearings or something's getting ready to go wrong. Maybe you can get by with just oiling it, but nonetheless, it's something that needs to be corrected. All right? And they need to find out what it is. We shouldn't get any smoke coming off of these things. We shouldn't have any scorching. We shouldn't have any soot that's being brought into the chambers or the heating units on there. They should be making a relatively clean burn when it comes to it, just like natural gas. All right. So things to look out for: 24-inch clearance between the burner and the combustible materials. Okay. The ignition transformer shouldn't be vibrating. Everything should be smooth. You'll find that dirt gets put around this air intake port right in here. And so that should be clean so we don't limit the amount of air that comes into it at all. There should be no oil leaking from any of these joints in here. So our pump should be working just fine. If you could see the flame do anything else, it should be more of a cone shape than anything else. Typical color is going to be yellow and orange when it comes in there. The primary controller, all right, the purpose of that is kind of like a reset button. And so basically our pump, our motor kicks on. So our thermostat calls for heat. Our motor kicks on. We start spraying oil into the unit. We're blowing oxygen in there. Our igniter is sparking. And we should start a fire. If we don't sense the fire, then the unit's going to shut itself down. The only way it's going to restart again is to go press this primary controller button and get it to restart again. All right. I'm going to suggest that you don't do that, and the whole reason is we don't know how many times that button was started. It's not our problem. I always remember, somebody once saying that, if this thing's broken, that's somebody else's problem. But if I start messing with it and trying to fix it, now I end up making their problem my problem. And it's not my problem. My job was to identify things that aren't working. Now, granted, if you're intimately familiar with these things and you know your way around them, have at it. You're a better expert than I am. But if you do have some weaknesses on them, like I do, then I wouldn't be resetting it. We turned it on. We made our attempt. It didn't operate, whatever the reason. It could be a bad igniter. It could be that I got dirt around that air intake, so I'm not getting any oxygen coming in there. It could be my pump is bad. It could be I'm out of oil. It could be a whole bunch of stuff. But if somebody went in there and they tried to restart this thing, and maybe they did it 3, 4, 5, 6 times, and now I go do it again, and now there's a whole bunch of oil that's in there, and I don't want to take a chance of an explosion or anything else like that. I'd rather just plead ignorance and say, I don't know, it's not working. Let's get a heating guy that's familiar with it to go ahead and fix it. Combustion air, I kind of used that term a little bit earlier, but we need to be checking for combustion air as it comes into our appliances to make sure they're working, or our gas appliances. So when I use the term appliances, I am talking about the furnace, the water heater. I'm even talking about a gas dryer or a gas stove. All of those, we're going to lump them together as appliances. Now, There are basic general rules of thumb to make sure that we have enough combustion air. So if I have a room that's big enough, I don't have to bring combustion air from another location. All right. And I'll show that slide in a little bit. But let's say I am in a small room and I want to start drawing combustion air into where our furnace is. Now this is a natural draft furnace. So up on top here, we do have a draft hood. There is no fan inside there. I'm not creating a draft when it comes through it. Combustion air is going to come in through the bottom, and that's what I'm going to be mixing with my fuel to go ahead and make my fire. The dilution air comes in through the draft hood, and that's what I'm going to be using to lower the temperature as it goes up and out the chimney. So combustion air where the fire is, dilution air where it goes up and out. We do need to look at the data plate that's on the furnace. You're going to find two numbers on the data plate. One number is going to be for the input BTU, and then there's going to be an output BTU. So the input BTU is how many BTUs I'm making with those burners that are there. So if I have a 80,000 input, or I'm actually going to use simpler numbers, 100,000 input BTU, all right, and an 80,000 output BTUs, that tells me that I have an 80% furnace. So 100,000 BTUs is made to create the fire. 80,000 BTUs are going into the house. That's my output. The other 20,000 or 20% is going up and out the vent. That 100,000 BTU is the number that I'm going to be using for my combustion air. If I'm taking combustion air from an inside source, all right, from another room inside the house, I can do that. I just need to have two openings that bring it into the house. So 1 square inch for every 1,000 BTUs up high, and 1 square inch for every 1,000 BTUs down low. So if this is a 100,000 BTU opening, I need to have basically a 10 by 10 opening. Now, because these grills eat up those spaces, a 10 by 10 isn't going to be big enough. All right. So typically we want to be about 25% more than what that is. I think I got another slide coming up a little bit that explains how much gets eaten up. I know with the wood grills, that's like, there's only 25% comes through, where it's kind of the other way around with the metal grills. So we do need to be significantly bigger. All right, 1 high, 1 low. So 100,000 BTUs, this is kind of the same example I just used. We need 100 square inches. Metal grills use 75%, so we kind of have to add on another third to get that 100% back up there. Wood grills are 25, so I have to do quadruple, to get to the 100% of that mark coming in there. 1,000 or 1 square inch for every 1,000 BTUs. That is if I bring the combustion air from another room that's already inside the house. Now, if I have a pipe that I'm bringing combustion air from outside the house, and I guess I should be a little bit more specific. It doesn't necessarily have to be outside the house, but it has to be outside the conditioned space. All right. So if I have an attic that's vented and open to the outside, I can bring combustion air into the room through that attic. That's completely acceptable. If I have a crawl space that's part of the exterior of the house, so it's in the unconditioned space, we're not heating it, we're not cooling it, we're not insulating it, I can bring combustion air from there as well. Typically, they're going to go through a sidewall, and they're going to bring everything from there. Now, those BTUs, the previous slide was 1 square inch for every 1,000 BTUs, where in this case, it's going to be 1 square inch for every 5,000 BTUs, all right? So at this point in time, we would just have, out of 100,000, divide by 5, that's 20. So I need 20 square inches instead of 100 square inches to give me the same amount of air coming to the outside. Usually it's going to end up being like a 6-inch duct, a 5-inch duct that comes out of there. We do want to have some sort of a damper on it so that, we're not losing heat. B, we're not flowing in air, cold air when the furnace isn't operating. This is only designed to bring the combustion air and the dilution air into the room when the furnace is operating. If I don't have any sort of additional combustion air coming in there, that's fine. It depends on the total amount of BTUs that's being used in that room. So if it's 100,000 BTUs, we need 5,000 cubic feet. In other words, 25 by 25 feet, based on an 8-foot ceiling. All right. The more BTUs, the bigger the room is. So for if you got an open, unfinished basement, that's a pretty decent size. And nowadays, our appliances are getting far more efficient than when we put these numbers together. It used to be like a 40,000 BTU water heater and a 100,000 BTU furnace, and we would need a 30 by 30 room in order to do that. And typically they wanted to have fresh air coming in from the outside. But everything's more efficient right now. We're not getting that point. So if we have an open basement, even if it's finished, as long as it's wide open, then we really don't have to have any sort of external combustion air coming in. This is a golden rule. Does need to be committed to memory. So combustion air, again, that's the air that I need to make the fire. Combustion air cannot be taken from a bedroom or a bathroom. All right. And that closet that's in the bedroom or the bathroom, even though it says it can't be taken from the closet, it all depends on how it's set up. All right. So if that door that we're looking at right now is an exterior door and it has weather stripping all the way around it, and when that door is shut, air is not passing through it, and we do have another combustion air source outside, that furnace located there is just fine. All right. If it was a high efficiency furnace with 2 pipes on it, one pipe brings in combustion air and the other pipe exhausts the used gases from the fire, I'm not using the room air for combustion air. I'm bringing combustion air through one of the 2 pipes. If that's the point, then that can also be put in there. Now, if this is a natural draft or an 80%er and that door has louvers on it or it's open on the bottom, and now I'm drawing combustion air from that bedroom in order to make the fire, that's when it's a problem. So the key word is using combustion air from a bedroom or a bathroom. Another term is scorching, and we're going to start getting into the furnaces real soon. Scorching even is any time that I'm burning something, for lack of a better term. So when in this situation, when I have it around the burner like this, that's a pretty strong sign that either I got a hole in the heat exchanger or I got one hell of a bad gas air mixture. And if I have like it's coming out of there too rich, maybe a pipe is broken and it's not drawing in enough oxygen to go ahead and ignite right away. So it pushes the gas and then the gas starts spilling out of that opening. It's going to eventually ignite, and when it ignites, it does create a flash that comes in there, and that flash is what ends up leaving the scorching marks. Sometimes we'll see rust marks on there as well. Another indicator that we're backdrafting, or at least air is rolling out of there. So scorching, flame rollout is another term that we're going to be using when the flame actually goes the wrong direction. This one's a little bit wider. You can see how it has that big cave that comes all the way across, or big arch that comes all the way across here. That's all scorching as well. Now this is on a hydronic boiler, and you could even see all the rust over here as well. So chances are we had a lot of flame rollout and it's coming up on the sides. It does bring with it a whole bunch of humidity. So, and it may have been fixed. We don't know. All we could do is identify what it is, give a probable cause, and then let somebody else come in here to do a diagnosis to it. All right. Going back to natural draft furnaces, I can't tell you when the last time I've ever done this, and I don't know if I ever will again. We used to take off the draft hoods and try and get inside the heat exchanger where the burners are and visually check it for holes or cracks in the heat exchanger. I'm going down memory lane here. I used to have this little dental mirror when I started, and I would aim it because right up on the underside or straight in the back, that's where you would find most of the holes and rusted out parts of the heat exchangers on there. And once the heat exchanger is gone, it's, you're done. You might as well just get a whole new furnace. Everything else is going to be 20 plus years old. And even with these old natural drafts, they're going to be over 25 years old. I can't, I may run into one that's still working, but I really haven't seen one in a long, long time. All right, so I think it would be very rare. But we would unscrew the flame rollout shield, get our mirrors inside of there, obviously, and look for any sort of rust, cracking, holes, and so forth. I ended up getting a plexiglass mirror. That was probably one of the smartest things I ever did. Get a plexiglass mirror that was like about 1.5 inches, 2 inches wide, and about 2 feet long. And then I would stick that right on top of the burner, and I would shine a flashlight. I kind of put the tip where my nose is so the beam follows my eyes, and it reflected off the mirror, and then I was able to see up inside the heat exchanger. And it gave me the biggest area that I could see with, and then I would tilt it up, so I get that reflection as it comes back and see the backside of that furnace. Reminiscing there. Nowadays, with the mid-efficiency and high-efficiency furnaces, we really don't even see the inside of the heat exchanger anymore. We may be able to see a small little section of it, and that's it. So we're kind of limited in what we can do with the furnaces. All right. So venting in this next section is going to talk about exhausting our bad gases after the fire. A little more terminology. I'd like you to know the difference between a flue, a vent, and a vent connector. All right. Flues, first of all, they have to conform to the 2-10-3 rule. That 2-10-3 rule is the height above a roof line that a top of a chimney or top of a flue needs to be. All right. So in other words, it has to be 2 feet higher than anything within 10 feet of it, and the minimum height above the roof line has to be 3 feet. All right. So 2 feet higher than anything within 10 feet. But if this is my roof, I have to be at least 3 feet and off the highest end of that roof. So if it's like a 412 slow pitch and I'm almost at the top of the roof already, so there's nothing within 10 feet of it at the top line of it, I still have to be 3 feet above that roof line. If it's a real steep pitch like this and the chimney comes up this way, then whatever is 10 feet away from that, then that has to be 2 feet higher than that 10-foot point. All right. In order for something to fall under those rules and be classified as a flue, it basically one of two things has to be existing. It has to be inside of a chimney. So it doesn't matter what the fuel is that I'm exhausting. As soon as I put it in a chimney, then it's automatically a flue. When it's a flue, it falls under the 2-10-3 rule. Also, if I'm exhausting wood or oil, it's automatically a flue, and it has to fall under the 2-10-3 rule. If it's natural gas or propane, all right, and it's not in a chimney, all right, so that's our second one up in here, all right, that's for our vent right here. They have their own requirements, and they could be as low as 6 inches above the roof line. Typically, we're going to see them around 2 feet. I do see where a lot of inspectors make a mistake, and they'll see a B vent that comes up through the roof, and they start calling out the 2-10-3 rule. It doesn't have to conform to that, all right? As long as it's natural gas and it's not inside of a chimney, then it doesn't have to conform to that. There is a chart. I know you could find it in the IRC and under the mechanical code section where it talks about the height for venting gas appliances. And that all has to do with the slope of the roof. So the steeper the slope, the taller it needs to be. The lower the slope, the less it needs to be. But there is no 2-10-3 rule when it comes to that. Vents for gas appliances, if it's a high efficiency, it's going to be a PVC pipe. If it's going to be a mid-efficiency furnace, typically that's going to be a B vent that goes up in there. Even the old natural draft furnaces, those are going to be also B vents that come in there. Those B vents, we'll get into clearances of those in a little bit. Those had a 1-inch clearance, where our vent connectors have 6 when it comes to gas. So that brings me up to the third item, the vent connector. This is the pipe that, let me back up. Most vents for the mid and natural draft, mid efficiency furnaces and natural draft furnaces, those are going to be a 2-wall pipe. So it's going to be a pipe, and then there's another pipe inside of it. And there's going to be a small air gap, usually about 1/4 of an inch in between there, so air is going to be able to flow between the two of them. That helps dissipate the heat, so I can get closer to combustible materials. A vent connector is going to be a single wall pipe. All right, and that single wall pipe is what connects the appliance to the chimney, or connects the appliance to the B vent, and that's called a vent connector. Single wall pipes, and these vent connectors cannot go through a structure. They can't go through a wall. They can't go through a floor. They can't go up and out through the roof. All right, they're just meant to connect to the B vent. They do have to conform to the same slope rules. We'll get to those in a little bit. But again, they can't go through a structure. So in this illustration, we're showing both a vent connector and a B vent. All right. So as I start over here, here's my appliance, and right above the appliance is my vent connector. This pipe is sloped upwards towards my B vent, and now I have the pipe within a pipe. The B vent can go through my structure and can go all the way through the house and all the way up through the roof. All right. This B vent, the way they're usually designed is I can get a 1-inch clearance to combustible. So even though I'm going through a structure, and this illustration kind of shows it touching, there should be at least a 1-inch. Vent connectors, this for natural gas, it's going to be 6 inches. I would like you to remember that, all right? 3 different numbers. Vent connectors can be used on gas, propane, oil, wood. They're going to be used on all of those. But the clearance from that combustible material depends on the fuel that's being burned. So vent connectors for gas and propane, and again, please write this down, 6 inches. Vent connectors for oil, 9 inches. Vent connectors for wood, 18 inches. So 6, 9, 18, those are the 3 magic numbers we need to remember. 6 for gas, 9 for oil, 18 for wood. This one's kind of a no-brainer. We're coming out of our water heater because I have a draft hood over the top of my water heater. I know that I'm going to be a gas appliance. So because I'm a gas appliance, that means I have to be 6 inches away from combustible materials. It's still supposed to slope upwards until it goes into the chimney. Anytime it goes downwards, like we're seeing in this picture, that's something that's going to limit the flow and be a high chance of backdrafting. When it comes to water heaters, when we look down at these escutcheon plates, which are pieces of plastic where the water pipes come into the water tank, they melt pretty quick and easy. So if I'm backdrafting at any time, or if I have backdrafted any time during this, I'm going to see those things melted. Length of a vent connector, typically under 5. There has to be some sort of an offset. We don't want to be going straight up and down. You know, once we start getting over 10 feet, we need to start being a little bit worried, all right? So we're going to be looking for signs that we're not venting completely and our air gases aren't going up there. Clues that that's happening is we're going to see condensation stains on the vent connectors or on the B vents. We may see some backdrafting signs like I talked about with those escutcheon plates, but we definitely want to look for it. These vent connectors are supposed to be the same size as the opening that comes out of the top of the appliance. We're not supposed to make them bigger. We're not supposed to make them smaller. They need to be the same size. And same thing when we go up to the B vent. Now they can get bigger when they connect with another appliance. So I could have multiple gas appliances. I could have multiple propane appliances hooked up to the same vent. I cannot mix fuels, however. So if I have a gas and an oil appliance, I can't mix those exhaust gases. They have to stay separate. Just the other day, I was called for a water heater and to verify that it was venting into the fireplace flue. And, I was in disbelief when the person called me and said that, they're doing an insurance claim and they want to make sure that everything's okay. And the person who's going to install the water heater said that it goes into the flue. And I'm like, well, that's not possible. People just don't do that. It was the case. So what I ended up doing was disconnecting the water heater vent connector where it went into the chimney. I ended up putting a flashlight in there. I went into the firebox and looked up the smoke chamber and looked up the flue, and sure enough, there was my beam right there for my flashlight. It was definitely coming right inside there. So there was no damage. The measurements worked out fine. There was only one flue going up and out the top. All the signs said, yeah, this is going in there. So now their solution is either to build a fireplace with a secondary flue going to the outside, or they can go ahead with a higher efficient water heater and just direct vent it straight out the sidewall. And I believe that's the route that they're going. So they're going to disconnect it from the chimney and then put that sidewall in there. So 3 screws are supposed to be holding all these connections together. They don't all have to be evenly spread out around a circle, but there do have to be 3 points of contact in a circle, and that's going to keep these things from twisting or flipping around. No openings, nothing where anything's going to become allowing carbon monoxide to enter the building, so it does need to be tight. When we put these sleeves in there, common sense says that I have to have the smaller pipe going into the bigger pipe as it goes up and out. If it's the other way around, then I'm going to leave a chance for carbon monoxide to be escaping between those 2 gaps. All right. We talked about clearances before. So natural gas clearance on a single wall pipe or the vent connector, 6 inches. Clearances for B vents on natural gas is going to be 1 inch. Now at the bottom down here, this whole pipe throughout here, this is my vent connector. And then right up in here is where my B vent begins. So you can see it's just a small little gap in between there. But that little gap allows enough air to go through and lowers the temperature of that metal so that I could get closer to the wood. I still have to maintain a 1 inch clearance. All right. In this case, it's actually touching. It's actually touching the wood. Now, granted, there was no burn marks or anything else on there, but it was still touching the wood, which is, going to be somewhat of an issue. Even with this insulation on the pipes or the refrigerant lines that come to the vent connectors. I just had one yesterday. 2 things on the vent connector. One is they had their suit that was in one of those plastic clothing bags, that you cover the suit to keep dust from getting on it. They had that hanging on the plumbing pipe that would drape it over the vent connector, and it was literally resting on the vent connector. So I'm curious, and I unhook it off the pipe and pull it away, and sure enough, all that plastic was melted right onto the pipe. It gets that hot. I mean, luckily their clothes weren't ruined at all, but I just couldn't leave it like that. So I brought it down and moved it to another location. And then they also had their air conditioning refrigerant lines also touching the vent connector. And that styrofoam insulation, basically this stuff over here on the right, that styrofoam insulation was scorched and melted as well. All right. Now, I hear the argument saying that, well, 6 inches is kind of overkill. I've seen so many times where things are closer than the 6 inches, and never has a problem ever really occurred. And I get it, and I've seen the same thing with my own eyes. Something's been there for 15 years. You would think I would have some sort of melting and burning, just like I described, that we see, and sometimes it doesn't happen when it's there. I get it. But those distances are not there for when the furnace is operating normal. They're there when something goes haywire. All right, they're there to be overly cautious, overly protective. It's not in our, when they set up these numbers and these clearances, it's not that, well, we want to reduce the chances of a house catching on fire. No, we want to make a logical clearance distance where there won't be any chance that a house will catch on fire. So because of which, I'm kind of a stickler when it comes to these things. Anytime I see a combustible materials such as the refrigerant lines, non-metallic cable wiring that comes in there, any sort of insulation that could be anywhere, wood structures of the material. If I'm within 6 inches, it's getting photographed, it's getting documented, it's going in our report. All right, that's my 2 cents.